Eli.
Hello. Okay, looks like it's time, past time actually. There's a bunch of people that had to be admitted to the Zoom today because so many groups have been quarantined across campus. So sorry, I had to take a little bit of time to get them all situated. Hopefully I'm not missing anybody. Okay, yeah, so we left off last time in our discussion of thermochemistry, okay? And we started to draw this apparatus here, which is used to determine the constant volume calorimetry of a specific system. Okay, so let me just remind you quickly what this thing is doing. Inside this little square right in the center here, this square here, we place some type of substance, and then we burn that substance in the presence of a known amount of oxygen, and the released energy is absorbed from the system into the surrounding water, and we measure the temperature in the water. Okay, and we basically measure delta T in the water. Okay, so we're observing the temperature change of the surroundings. Okay, so we're observing the temperature change of the surroundings, which means that the system itself is providing the Q or the heat in order to heat up the surroundings. Okay? We can actually measure the energy, the total energy of the system, the total energy change of the system, so delta E, if we know the heat capacity of the system itself. Okay, so if we know the heat capacity of what's called the calorimeter, then we can solve for the delta E of the system. Interestingly enough, this thing is called a Baum calorimeter. And even though it sounds pretty cool, it's not as cool as it sounds, okay? And the reason it's called a Baum calorimeter is because essentially what's happening inside this chamber is you're not allowing any of the gas to expand, okay? So you've essentially created a mini bomb inside this thing with a highly pressurized capsule. Now, you're not burning enough material to actually cause the capsule to rupture and explode. Otherwise, this would no longer be constant volume. So you're forcing the volume to stay small, but you're igniting a small amount of propellant. Okay? So this is called Baum calorimetry, is constant volume calorimetry. And we can measure the Q that enters into the calorimeter. We're going to call this Q cal. Q cal is just equal to the heat capacity of the calorimeter multiplied by the change in temperature that we observe in the surroundings. Okay, so we can directly measure the heat that's entering the calorimeter from the system that's igniting in the middle. Okay, this is the temperature or the heat that's absorbed. And this is absorbed by the entire assembly. Okay, so the heat absorbed by the entire assembly is equal to this Q Next, we have the heat capacity of the entire assembly. Okay, that's C cal. And delta T is the observed temperature change of the water. Okay, so that's what this temperature probe is giving us. Essentially the change in temperature that's elicited by this chemical reaction. We know that all of the change in temperature comes about because of heat that's being released by the reaction that's happening inside the system. So we can say then that Q cal is equal to the negative of the Q of the reaction. Okay. We know that all of the heat that's going into heating up the system is coming from the reaction itself. Okay. What's being released and absorbed by the surroundings must be released by the system. Okay. So Q reaction is just equal to the negative of the Q cal. And another interesting bit, at constant volume, right? At constant volume, we're not doing any PdV work. We're not doing any change or pressure volume work, right? So this P times the change in volume term that's in delta E, this is equal to 0 because there's no change in volume. So we know that delta E must be exactly equal to the Q. And so we can say that Q reaction is equal to the delta E for the reaction. Okay, so then delta E reaction, putting all this together, is equal to negative Q cal is equal to negative C cal times the change in temperature. So we're directly measuring the total change in energy of the system by measuring only the temperature that is happening within this entire assembly. Pretty amazing. Let's do an example of this. By the way, bomb calorimetry is something that's fairly common to see. We don't do any experiments with the bomb calorimeter in Gen Chem, but as we get into higher level chemistries, there are a few, especially in PChem, physical chemistry, where we start to do some experiments with bomb calorimetry, and you actually get to measure the delta E of a reaction. Okay, but there are several examples in the textbook, and I believe some of the homework problems deal with bomb calorimetry as well. So let's go through an example here. Inside the bomb calorimeter, I place 1.010 grams of sucrose. Okay, sucrose is just a complex sugar. Actually, it's a fairly simple sugar. With a formula of C12H22O11. Okay, that's the formula for sucrose. And we're going to combust this in a bomb calorimeter. We observe that the temperature goes from, let's see, 24.92 degrees Celsius. That's the starting temperature. And it heats up to 28.33 degrees Celsius. Okay, we want to find the delta E for the reaction in kilojoules per mole, given that the heat capacity of the calorimeter is equal to 4.90 kilojoules per degree C. Okay. We're given all the information that we need here. Essentially, we need to go back to the delta E is equal to the negative times the C cal equal to the negative C cal times the change in temperature. So we need the delta T. We're given the heat capacity of the calorimeter itself. So all we need is the change in temperature. So delta T is equal to the final temperature minus the initial temperature. So 28.33 degrees Celsius minus 24.92 degrees Celsius. And this gives us plus 3.41 degrees Celsius. Okay, so we've increased the temperature by 3.41 degrees Celsius. Okay, next is pretty simple. We can calculate the Qcal is equal to the heat capacity of the calorimeter, which is 4.90 kilojoules per degree C, multiplied by the change in temperature, which is plus 3.41 degrees C. Degree C cancels out and we're left with kilojoules. And we find that this is plus 16.709 kilojoules. Okay, where the 7 is the significant figure. Okay, so that's the Q of the calorimeter. Basically, that's the energy that the calorimeter has absorbed. So the surroundings have absorbed this energy. Therefore, we can say that the reaction gave off that energy and had to come from somewhere. So Qcal is equal to negative Q reaction. Okay, so Q reaction is equal to negative Qcal, is therefore equal to negative 16.71 kilojoules. So Q reaction is equal to negative 16.71 kilojoules. And we know, since this is constant volume, that delta E reaction is equal to the Q of the reaction. So we can say that delta E reaction is equal to negative 16.71 kilojoules. But we're asked to give the delta E reaction in terms of moles of sucrose burned. Okay. We need to normalize this by the number of moles. So we have to calculate the number of moles. We're given that we have 1.010 grams of C12H22O11. We just need to multiply that by its inverse molecular weight. Okay, so we have 1 mole of sucrose divided by 342.3 grams. Okay, and this is, of course, the number you can get by adding up all of the atomic masses of each of these elements within this molecule itself. I just did it here because that should be pretty routine for you by this point. Okay, so grams cancel out, we end up with moles, and this number becomes 2.95 times 10 to the negative 3 moles. Oops, I need a few more digits there. 2.9506, where the 0 is the last significant figure. Okay, so this is how many moles we have. To get the kilojoules per mole, all we have to do is divide that initial delta E by the total number of moles that we have here, and we have kilojoules per mole. So we take delta E reaction, and that's equal to negative 16.71 kilojoules. We divide that by the moles, 2.9506 mole, times 10 to the minus 3 moles, and we get negative 5.66 times 10 to the 3 kilojoules per mole. Okay, that's our delta E reaction for this system of sucrose. That means that if we burn an entire mole of sucrose, so 342.3 grams of sucrose, we will release a total of 5.66 times 10 to the 3 kilojoules of heat energy. Okay, that's how much heat will come off of this system. okay? And typically, if we're talking about delta E for a specific reaction, it's going to be normalized by moles, okay? And it's going to be normalized by moles because this type of number is going to be, it is an extensive number, meaning that it's going to change depending on the amount of substance that you have. Okay, so if I had 2 grams of glucose or sucrose, this would be a different number. So I need to normalize the energy that I get out by the number of moles, and then I can use that number basically with under any circumstance, because I've normalized by the total number of molecules. Okay? So that's Bohm calorimetry, constant volume. What about constant pressure? To talk about constant pressure, we need to introduce a new concept, and this is something called enthalpy. Okay, enthalpy. Enthalpy is given the symbol of H. Okay. And enthalpy is equal to H is equal to energy, total energy, plus P times V. Okay. All 3 of these are state functions. Energy, pressure, and volume. Okay. And if we set this to constant pressure, then we can write this as delta E is equal, or excuse me, delta H is equal to delta E plus P times delta V. Okay, and the reason I'm not saying delta P in this case is because pressure is constant. So pressure is constant here, so that means that we only need to consider one pressure variable. We don't need to consider the final and the end point because it's always going to be the same. So we have delta E plus P times delta V. Delta E, recall, is equal to Q at constant pressure plus work. And that little subscript P indicates that the Q is happening at constant pressure. Okay, that's all that means. And of course, P delta V is equal to negative work. Okay. So then that therefore means that at constant pressure, the change in enthalpy is equal to QP. Okay, it's simply equal to the heat energy of the system itself. Okay, so delta E is equal to Q and at constant volume, and delta H is equal to Q at constant pressure. They seem pretty similar enough. Delta E and delta H are very similar, but not the same. Okay, they're not the same, but they are very often similar. Let's compare the two. Delta E is a measure of all of the energy. Okay. It's a measure of all of the energy, so Q and W, that's exchanged with the surroundings. Delta, ooh, well, that's a bad delta. Let's try that again. Delta H is a measure of only Q. Okay, at constant P. Now, why is constant pressure such a useful thing to talk about? What's up? We can control it, but what is essentially every single reaction that you're going to do, what are the conditions that are going to be true? It's going to have atmospheric pressure, which is constant. So essentially, every single chemical reaction, unless you're doing a reaction inside a bomb calorimeter, every single chemical reaction will have a constant pressure associated with it, okay? Which makes this such an easy thing to talk about. So under most conditions, any type of chemical reaction that you will do will be constant pressure. And therefore, you can say that delta H is equal to Q. Okay, so in general, for reactions with a small or not very large delta V, okay, so if the reaction itself doesn't change volume so much, delta E and delta H are basically equal. Okay, very close to being equal, if not exactly equal. Okay, but for reactions with a large delta V, delta E does not equal delta H. Okay, they're slightly different. And this has to do with the pressure volume work that's associated with change in the change in total energy, delta E. Let's do an example of this. Okay, imagine I have a butane lighter. I did have one in my pocket, but it's no longer there. I don't know what happened to it. Okay, I'm lighting a butane lighter. Okay, I'm lighting a butane lighter, I'm holding it on. 1 mole of butane produces 2,658 kilojoules of heat. And remember that this is a combustion reaction, okay? So you're taking butane, you're combusting it, you're creating more moles of material. Therefore, you have to expand that gas against the atmosphere. So this is a gas-producing reaction. You're expanding that gas against the atmosphere. Therefore, you're doing work. There is a change in volume associated with this reaction. And the work is equal to 3 kilojoules of work. Okay, so 3 kilojoules of work are being performed on the surroundings. What are delta H and delta E for this reaction? Okay, let's compare the two. Delta H is very easy. Delta H is just equal to the amount of Q, right? Because this is at a constant pressure. We're just burning the butane in the constant atmospheric pressure. So we know that the H, the change in enthalpy, is going to exactly equal the Q. That means that this is going to be negative 2,658 kilojoules. And I know that it's negative because if I'm talking about the specific system of the butane, the reaction that's happening here, it's giving off 2,658 kilojoules of energy into the surroundings, and that had to come somewhere. Okay, so the surroundings is receiving 2,658 kilojoules. Therefore, the reaction is losing that 2,658 kilojoules, and that's why that sign is negative. Let's calculate delta E. Delta E is equal to Q plus W. So this is equal to the system is giving off 2,658 kilojoules of heat. So that's negative 2,658 kilojoules of heat. And then we have to add the amount of work that the system is doing on the surroundings. Okay. Again, this has to be negative because the system is doing the work on the surroundings. So the system is losing energy by doing work on the surroundings. So this is negative 3 kilojoules. And we find that delta E is equal to negative 2,661 kilojoules. Okay, so the two are close, right? There's a far more energy that's coming out from the heat energy itself, but they are slightly different. And they are slightly different because there is a change in volume associated with the reaction. Okay. So in this case, delta E does not equal delta H. Okay, since most reactions are going to be occurring at constant pressure, we oftentimes use delta H rather than delta E. Okay? Delta H is much easier to work with. We don't have to worry about the change in volume. So we typically use delta H to talk about how much heat energy a reaction is going to produce. So let's talk a little bit more about delta H and what it actually means. A reaction can have positive delta H or negative delta H, just like a reaction can have positive delta E and negative delta E. When a reaction has a positive delta H, that means that the reaction absorbs energy or absorbs heat from the surroundings. Okay, so the system is absorbing heat from the surroundings. It's gaining heat energy. Therefore, the Q is larger than what it was when it started. Therefore, delta H will be positive. Okay. In the case where we have a negative delta H, this means that the reaction is giving off heat. To the surroundings. Okay, it's giving off heat into the surroundings. It's losing heat energy and pumping it out into the surroundings. Okay. In this situation, the reaction feels cold. Okay. It feels cold because it's taking the heat energy out of your hands and putting it towards the reaction itself. So it feels cold. And in the negative case, the reaction feels warm or hot. And that's because it's shedding energy from itself and it's pumping it out into the surroundings, and your hands that are sensing that heat are part of the surroundings. When you have a positive delta H, this is called endothermic. Okay, endothermic. And when you have a negative delta H, this is called exothermic. These root words here are Greek. Endo meaning inner. Okay, so there's an inner heat. Thermic, of course, is heat. So in the case of endothermic, there's an inner heat. That means that it's pulling the heat in. Okay, exothermic means outer heat. So this is outer. Essentially, it means that it's pushing the heat out. Okay, so we have exothermic and endothermic, and you'll see those terms very frequently for the rest of the semester. So I would learn this pretty astutely. Let's do some examples. We did this example in, I think, chapter 1 when we talked about state changes. We want to identify whether each of these processes are exothermic or endothermic. How about if we have an ice cube melting on the counter? So I took an ice cube out of the freezer, I put it down on the counter. What's happening here? Exothermic or endothermic? This isn't a reaction, it's just a state change. Endothermic. You think it's endo? Does that make sense for everybody? Right? This thing is pulling in heat from the surroundings, pulling in heat energy. If you touch it, it's cold. It's absorbing that energy from your hand, and it's putting it towards that state change. This is an endothermic process. What about iron oxidation? This is what's happening in hand warmers, right? You're oxidizing the iron very quickly and you're releasing all of that energy. So then this therefore must be what? Exothermic. This is exothermic because it's releasing heat energy from the system into the surroundings. Okay, so in the case of an ice cube melting, the delta H is positive. In the case of iron oxidizing, the delta H is negative. Okay. Now we need to ask kind of more of a basic question that we haven't really discussed yet in any real way. Where does this thermal energy come from? Okay. We have iron. Let's go back to our favorite exothermic reaction. We have oxygen. And we produce Fe2O3. Careful, this is not a balanced equation. We start with iron chunk that's at 0 degrees Celsius, for example. Say we're outside and it's really chilly. And we start with oxygen that is also at 0 degrees Celsius, the same temperature as the ambient surroundings. And then all of a sudden, when we make the iron oxide, this then becomes plus 60 degrees Celsius. Really warm. Okay, it's really warm. Where is this energy coming from? The thermal energy that's released comes from the chemical energy that's stored within the position of each of these constituents that's going into the reaction. So each of the reactants has some sort of chemical energy associated with it, okay? Just like potential energy, and it releases that chemical energy upon reacting. So thermal energy comes from the chemical energy that's stored in the chemical bonds. Or in the positions of electrons and nuclei. Okay, so we're rearranging these nuclei and electrons, and that rearrangement results in a decrease in energy, so you're lowering the energy of the system. The difference in energy from the starting point to the ending point is large, and so it releases that energy. That energy has to go somewhere. It can't just disappear, so it gets released into the surrounding. Okay, so that's where the thermal energy is coming from. We want to be able to quantify the amount of thermal energy that we expect that comes out of a reaction. Okay, so we want to be able to look at a reaction and say, okay, I expect this reaction to give so many kilojoules of heat per mole of reactant. Okay, we want to be able to do that so we can directly predict what's going to happen in a chemical reaction. The way that we do this is through the enthalpy of reaction. Okay, the enthalpy of reaction. And the enthalpy of the reaction gives us this information. Essentially, how much heat energy can we hope to release? Okay, thanks. The certain amount of heat energy that's released by burning or by reacting a certain amount of reactant. Okay. We're going to call this delta H reaction. I know, a little tricky there. Maybe a curveball you didn't expect. Okay, this is just delta H reaction. And this is an extensive property, meaning that it depends on the amount of reactant. Okay, so it depends on the amount that you're reacting. So we have to be very careful about this. Because it's extensive and because it's specific to particular chemical reactions, delta H reaction is almost always given with respect to a specific stoichiometric chemical equation. Okay, so it's usually given with a specific equation. So for example, let's burn some butane, C3H8 gas reacts with oxygen gas to produce 3 carbon dioxide gases plus 4 H2O gases. And the delta H reaction for this particular reaction is negative 2044 kilojoules. Okay, so this is based entirely on the stoichiometric amounts in this balanced equation. So I'm only giving this value in kilojoules, but it's based entirely on the stoichiometry of the problem itself, of the reaction itself. Okay. If you just give this number, then it's incomplete. You don't know what the reaction is that this delta H reaction is dealing with. Okay. So you have to be given both pieces of the puzzle to be able to use delta H reaction. What this means is that for this reaction here, if we carry it out exactly as it's written, so if we take 1 mole of propane and we burn it in the presence of exactly 5 moles of oxygen gas, we will get 2044 kilojoules of heat energy out of the system. Okay, so we can write this in terms of per mole. So this is delta H reaction per mole of propane is equal to negative 2044 kilojoules over 1 mole of C3H8. Okay, we can also write this in terms of per mole of oxygen. So delta H reaction over mole of O2 is equal to negative 2044 kilojoules per 5 moles of O2. Okay, so this extensive property has been normalized by the stoichiometric coefficients in the chemical equation. Okay, let's do an example of this. Let's do an example. This is pretty simple, and I want to show you that it's pretty simple. So let's take a barbecue grill. Okay, all of you have at least seen a barbecue grill being operated in your lives, right? You have this tank of propane, and then you have the grill, and you light it, and you burn meat with it, and then you eat the meat. It's great. Okay, so let's say that we have measured the mass of propane that's in the tank. So we measured the mass of the empty propane tank, and then we filled it up with some amount of propane, and then we measured it again. We subtracted the empty weight, and this gives us the total amount of propane that we have in the system. Let's say that we have 13.2 kilograms of propane in our tank, in the barbecue tank. Let's calculate how much heat we can release when we burn all of it. Okay, how much heat can we release if we just turn on the grill, crank it up, and just let it sit until all of this propane is burned? All of that heat energy from the reaction itself is being released into the surroundings, okay, so into the grill itself, and then out into the air. We want to calculate, in this case, the total amount of Q, or total amount of heat that's being released. And remember, at constant pressure, this is just equal to the delta H. Okay, so Q, heat, is equal to delta H at constant pressure. This is a constant pressure reaction. We're not increasing or decreasing the pressure of the surroundings of the atmosphere by burning this stuff. So we can use delta H. But we want to calculate the delta H total. Okay? And the delta H total is related to the delta H reaction through the stoichiometric coefficients that were given in the reaction itself. So first, we have to calculate how many moles of propane we have in the tank. And then we can use the stoichiometric coefficients in the reaction itself to calculate how much heat we can expect to produce per mole of propane. Then we can multiply it by the total number of moles of propane, and we get the total heat. Okay, straightforward. So we have 13.2 kilograms of propane. We're going to multiply this by the conversion factor for grams to kilograms. So this is 1,000 grams divided by 1 kilogram. Kilogram cancels out. Now we're in grams. Now we can use the molecular formula that we can get from the periodic table. So we multiply this by 1 mole of C3H8 divided by the molecular weight, which is 44.09 grams of C3H8. Gram cancels out. Now we're in moles. Okay. Now we need to use the conversion of essentially delta H reaction to total number of moles that we get from the stoichiometric equation that we have above. Let's look up here. So it's negative 2044 kilojoules of heat energy per 1 mole of propane that's burned. So then we multiply this by negative 2044 kilojoules per 1 mole of C3H8. Moles cancel out. And if I just take 13.2, multiply it by 1,000, divide by 44.09, and then multiply by negative 2044, I get the total heat energy that's released by burning all of this propane. And this is equal to negative 6.12 times 10 to the 5 kilojoules. That's a lot of heat energy, which you would imagine is true. If you burn 13 kilograms of propane, it's going to release a lot of heat, right? The grill is going to get super hot, and it's going to stay super hot for a really long time. Okay. That's delta H reaction. We're going to use this very frequently in this course. So I would learn this concept and how it relates to the actual stoichiometric equation. By the way, in the back of the book, there's an entire table of delta H reactions for different reaction types. Okay? And we'll get into, towards the end of this chapter, exactly how to use that table. Okay, but this is a value you're not expected to remember. This is a value that you're going to look up in a table. Okay, so I'm never going to expect you to remember the delta H reaction for propane, for example. I will either give it to you or give you a table, and you'll be able to figure it out from that table. Okay. Okay, so we have constant volume calorimetry that we talked about previously. That's the Baum calorimeter. We want to come up with a way to do constant pressure calorimetry, okay? Because constant pressure calorimetry is a little bit easier to do. We don't have to worry about keeping everything contained. And it's also more applicable to enthalpy, the change in enthalpy, which is what we've determined is the easier thing to talk about when we talk about the thermodynamics or the thermochemistry of a specific reaction. Okay, so we want to come up with some way to measure the calorimetry of a system under constant pressure. And the way that we do this is something called coffee cup calorimetry. I'm not making this up. coffee cup calorimetry. And actually, we will be doing this in the lab in a few weeks, I think. We will be doing this in the lab, and it's pretty straightforward, and it's also very self-explanatory, okay? We're gonna do calorimetry inside of a coffee cup. So we have our little Dunkin' cup here. There we go, okay? And inside this cup, we have some amount of water. And in this water, we're putting some sort of temperature probe. Okay, so we're measuring the temperature of this water. And then we carry out some reaction in the water itself. Doesn't matter what the reaction is, simply putting something in that's going to change the temperature and react. And then we measure the change in temperature of the water itself, and we can relate that back to delta H. So the Q of the solution, so whatever's happening inside this mixture, is going to be equal to the mass of the solution multiplied by the specific heat capacity of the solution multiplied by the change in temperature. Just like we had for the constant volume calorimetry, it's very similar here. Okay, we know that the reaction, whatever is happening inside the solution, is exactly equal to the negative that we get out into the calorimeter itself. So the reaction is equal to, the Q of the reaction is equal to the negative of the Q of the solution. Okay, so directly what we're measuring the heat output or input from the reaction itself. Okay, so we can say that this is the opposite of what's happening in the reaction. Okay, and because this is at constant pressure, we can say that the Q reaction is equal to the delta H of the reaction. So just as we were measuring delta E for the reaction in the case of the bomb calorimeter, we're now measuring delta H for the reaction inside the coffee cup calorimeter. And this setup is, as you can see, very simple and very easy to actually set up and to do, provided that the system is fairly insulated in terms of temperature. Okay, you don't want to have some metal cup that's going to basically take this heat energy and then transfer it into the environment rather quickly. You want something that insulates that temperature so you can get a good temperature reading. Okay, but assuming that that's true, this is a fairly easy, fairly straightforward setup. Okay, and just as we did for delta E, which was also an extensive property, we have to measure this in terms of the total amount of reactant that we're putting in. Okay, so this is going to give us a delta H per mole of reactant. Okay, so we always want to normalize delta H and delta E, otherwise they're kind of meaningless. So just to recap, the bomb calorimeter, measures at constant volume. It measures delta E. Okay, and then the coffee cup calorimeter at constant pressure measures delta H. Okay, so we have two different methods for measuring delta E and delta H. Okay, the next part is way too long to get into now, so I'm going to break here. You guys get an extra 5 minutes to your day. I sent out an email, but I just want to recap that email. The homework 5, I never gave an option to actually submit the thing online. My bad. I went back in and I checked the little box that I need to check, so now you should be able to submit a PDF. If you've already emailed me a PDF or pictures, please resubmit it to Canvas so that I have everything in one spot. Okay? I also extended the deadline, so it's not due until noon, but even if you submit it afternoon, I'm not going to care. So just submit it sometime today and you'll be good. Okay. Have a great Monday.